quality, we would ask everybody to mute your microphones, and except for Vint, please close your video. We have the open chat open. You'll see on the left-hand side. If you have any questions for Vint, please type them in. The game plan today is Vint's going to present, and then we're going to give ample time at the end, whenever he decides to finish, to answer your questions. So that is a bit of housekeeping we'll start with. So again, this is one of our weekly sessions. This is our history session. As I mentioned earlier on, we'll have Steve Crocker coming in September. We've had Marilyn Cade as one of our speakers, Olivier Crepin-LeBlanc, Wolfgang Kleinbacher. So this is part of our great series on the history, and they're providing their perspective, their experience on the history of internet governance. The recording will be edited and produced and give us 24 to 48 hours to make sure that's available. And the last thing I want to mention is please complete the online survey that we'll post into the chat as well. Okay, so just leading up to next week, we'll have Nick Smith and Keith Dravik. He'll be coming in with VeriSign, speaking on the internet governance actors. Now, everybody sees how good looking Vint is, and I just want to point out that this is what he looks like. And I've never seen him without a suit. He's absolutely impeccable every time I see him. But, you know, I asked Peter, I said, Peter, you've known Vint for a long time. In fact, your book on the internet in Brazil, I believe Vint did the preamble for that. And so I said, can you please share us some pictures of him where he was less polished looking, you know, like a regular guy. So he came up with this. So this is the only picture, Vint, we found of yourself without a suit. So it says 1956. I assume that was in high school?
No, actually, I would have been 13. So that would be 8th grade.
So you didn't get into your fashion statement yet, but you can, yeah, you have a mischievous look to your eye. Was this when you were in California or in Ohio?
I was in California. I was never in Ohio. My father grew up in Ohio. I started out in Connecticut, in New Haven, but we moved to Los Angeles in 1946. So I would have been 13 at the time that this picture was taken. And I was in California, just in north of Los Angeles.
So your descendants came from the great state of Ohio, the land of a lot of great inventors. So there's the connection for Ohio. Okay, so I think, do I have okay. Again, this is your James Bond look before you got into the cravat. So very suave as well. And it looks like the pipe look. That looks very good. So I'm going to turn over to you, and you tell me the next slide and we'll go on.
Well, then this is basically an attempt to describe what I've learned while the internet has been evolving. So I hope there'll be a few useful things to come out of this, and some of which will be related to internet governance, but a lot of it is related to the evolution of the internet itself. So let's go to the next slide. When Steve Crocker comes to talk to you, I hope he'll show you this slide, because this is what the ARPANET looked like just at the very beginning. There were 4 nodes that were put up starting in September, and then month by month nodes were added until we had the first 4. Steve was responsible for running what was called the Network Working Group, and its primary challenge was figuring out how to get computers of different types, and you can see how varied they were, to talk to each other through this homogeneous ARPANET. The blue dots here are called interface message processors. Today we might call them routers, although they weren't running anything close to the internet protocol. They were running a native protocol that was developed by Boll, Beranek and Newman, the company that built these things for the Advanced Research Projects Agency. One of the primary architects of the network was Robert Kahn, who later, of course, had a key role in the development of the internet. So I was a graduate student working on the Sigma 7 at UCLA at the time. And my primary job was to measure the performance of this small network and compare it to predictions that were made using queuing theoretic models that Len Kleinrock, a professor at UCLA, had his students developing, so we could compare the real world measurements with the predictions from queuing theory. And that was very helpful because a lot of those predictions were useful in designing and growing this ARPANET backbone, and eventually, of course, the other networks of the internet. Let's go to the next slide. Now, and here we were celebrating the 25th anniversary of the ARPANET in 1994. It took us all day to do the backdrop and to go find the zucchinis and the yellow squash and the coffee tins to demonstrate how primitive networking had been in the 1960s. You see John Postel and Steve Crocker and me in this picture. This was intended to be a geek joke. And if you look carefully at the way the network works, you'll notice that it's either ear to ear or mouth to mouth, and there is no mouth to ear. So this network would never work. But we figured the geeks in the readership of Newsweek would get the point. Next slide. So this is probably one of the most important tests of the internet in 1977. Bob Kahn and I started working on this in 1973. We published a paper in 1974 describing how it could work, and then began working on 3 different networks. The ARPANET already existed in 1973. It had been around for 4 years at that point, and had been extended into Europe by way of an internal satellite link on the ARPANET. So there was a link that went to Norway and then a landline down to University College London. There was a packet radio network which had been built, again, all under DARPA support in the San Francisco Bay Area. And so we had, and in addition to that, we had a packet satellite network, which was a shared satellite channel on Eutelsat 4A over the Atlantic, linking the east coast of the US with the west coast of Europe. So we had 3 different packet switch networks, not counting Ethernet, which was running at Xerox Palo Alto Research Center about a mile from my laboratory at Stanford. So there was a 4th packet network type, although it wasn't exercised in this particular demo. But this was a very important demonstration for me. I was, at this point in 1977, a program manager at DARPA running the internet program, packet radio and packet satellite program, and packet security program. And I wanted to show that the TCP IP protocols could actually work across multiple different types of packet switch networks. So we did this demo with the packet radio van going up and down the Bayshore Freeway, radiating packets going through a gateway, which today we might call a router, between the packet radio network and the ARPANET, went all the way through the ARPANET and then hopped out in London to go to the packet satellite network, which then went over the Atlantic back into the ARPANET in the US, and then across the ARPANET to USC Information Sciences Institute. There was actually, there were 2 satellite hops here, and they were both synchronous satellite hops. So the packets went 100,000 miles altogether to get from the Bay Area down to Los Angeles, which is only 400 miles away. But packets had to go through those 2 synchronous satellite hops, and it actually worked. And I remember leaping around in my office screaming, "It works, it works," you know, like it couldn't possibly work. It's software, and it's always a miracle when software works. So this was a very important milestone, at least from my point of view. Next slide. Well, I'm skipping over almost 9 years here, because what you're seeing here is sort of 1988 demonstration. That's more than 9 years, 11 years. In the intervening period, we turned the internet on officially in 1983, January 1st. With the ARPANET, packet radio, and packet satellite networks operating. By 1986, NSF had started to get involved in networking. They had the CSNet starting in 1982, and then in 1986, they started building the NSFnet. The picture you're seeing here is what it looked like. By 1988, they had multiple regional networks, a dozen or so of them interconnected to the NSFnet backbone. they were taking advantage of the fundamental design of the internet, which was to allow multiple networks to be interconnected to each other and traffic to be routed between any computer on any of the networks to any other computer. I don't think I have pictures of it, but around the same time frame in the mid to late 1980s, the Department of Energy built the ESNet, the Energy Sciences Network, and NASA built the NASA Science Internet. And so the US government in the late 80s had 4 internet backbones that were all interconnected through federal internet exchanges, plus the dozen or so intermediate level networks that were part of the NSFNet complex. By that same time, in the mid-1980s, we were starting to see other academic networks popping up, especially in the northern part of Europe, the Nordunet, for example, among others. So this period of late 1980s and early 1990s was a time of rapid growth of internet in the academic community, and the beginnings of that growth in the private sector. Around 1989, the first commercial internet services were put into operation in the United States, the UUNet, PSINet on the northeast part of the US, which covered the rest of the US, and then SurfNet, which was operating in the San Diego area, linking academic institutions together. Next slide. So this is the picture of the internet now. Actually, it's an old picture. It was derived from the Border Gateway Protocol backbone forwarding tables. But the idea here is the different colors are the different networks, of which there are literally tens of thousands, if not more, all interconnected without any top-down guidance at all, except for please follow the TCP/IP protocol rules, please follow BGP. The operators of these networks have different business models. Some are non-profit, some are for-profit, some are commercial, some are government-run. Some of them are, just in your house, your Wi-Fi system connecting to an internet service provider. They decide what software to run. Excuse me. They decide what hardware to choose. They decide who to connect to based on whatever terms and conditions they're willing to agree to. There's no top-down forcing function here at all, except for following the standards. The only coordination that's been required is to make sure that we do unique assignment of IP address space and domain names. And that is now done by the Internet Corporation for assigned names and numbers. Although in the early days of the internet, that was done by one guy, John Postel, with a big notebook. But eventually the scaling of the system, which by the way is pretty amazing. It's grown by a factor of over 1 million since the time that we turned it on in 1983. There aren't very many architectures that can scale by that amount, both in all dimensions, number of devices, number of networks, the bandwidths that we're operating at, which started at 50 kilobits a second for the ARPANET backbone, and now is 400 gigabits a second in many of the optical fiber networks, and probably will get to a terabit at some point. So this is a gigantic global collaboration that is fully distributed. Next slide. I don't think I need to tell anybody here how this works. This was just to show you that when people ask me, how does it work? I try to find a simple analogy, and postcards turned out to be very useful. So if you're struggling to explain how this thing actually works, you can just tell people it looks like electronic postcards, but it runs 100,000 times faster than the post office does. And the TCP protocol sitting on top essentially performs the same function that you would have to perform if you had to send a book to somebody only using postcards, because you'd be tearing pages out, you'd be cutting them up to fit on the postcard, you'd be numbering every page or every postcard to put them back in order, you'd keep copies to retransmit if anything got lost. So the TCP really performs a function which is very close to this analogy, and everybody understands that. The second point I want to make here about the success of the internet is that the internet protocol layer has 2 pieces of ignorance which have made it so powerful. The first thing is that the packets at that layer don't know how they're being carried. So when new technologies come along, you can just sweep the new technology under the IP protocol and just carry the internet packets on anything. So when optical fiber became available, it was no big deal to slide that underneath and support the IP layer protocol. The second thing is that the internet packets don't know what they're carrying. So the bits that are in the payload are uninterpreted by the network. They're interpreted by the computers at the edge of the net, which meant that every time you added a new protocol or a new application, you didn't change the network because the network was insensitive to applications, except possibly for the fact that the network had to have enough capacity to support the application, which is why back in the early days in the 1980s, we had a little bit of video and a little bit of audio that we were experimenting with packet voice and packet video, but we couldn't carry very much of it. Today, of course, there are huge amounts of video and audio being transmitted through the network, just as we're doing right this moment. But that's all a consequence of increased absolute capacity in the system. Next slide. This is where we start to get into the governance aspects of internet. I would say that there isn't time, of course, to go through every single one of these in detail. But I just want to draw your attention to how some of the applications of the computers and the internet are raising the stakes for the performance of the system and its reliability. So I would say here you see in the Internet of Things and AI and machine learning, people who are relying on these are assuming that it's reliable, safe, private, secure, interoperable, and has the ability to operate autonomously, by which I simply mean that if you have a house full of the Internet of Things and the internet connection breaks, the house still works. We want the system to be autonomous from the internet so that if the internet goes away, it still functions. Maybe you can't do some configurations and other things that might require access to the cloud, but at least your house keeps working. But those desirable features are very important, and people are worried that they may or may not be satisfied, all 5 or 6 of them. So that's a big issue. One wonders, are companies compelled, or should they be compelled to meet certain minimum requirements along those lines? Should they experience liability, for example, if they fail to meet the requirements or meet the standards, not all of which exist today? So that's one big issue. Another big issue has to do with the next bullet: misinformation, disinformation. Here we've seen the side effects of the rapid propagation of misinformation and disinformation, especially in the social media that are supported by the internet. And one worries that there is a dearth of critical thinking. People are accepting this misinformation and disinformation without giving serious consideration to its validity. And I think there are many people, including you, I hope, who are concerned about how to reduce the level of misinformation and disinformation in the network, or at least increase resistance to it, while enhancing the valuable qualities of the internet: freedom of access to information, freedom to share content, freedom to discover that information. So we are now, I think, confronted with some big challenges in this online environment to cope with these kinds of problems, because they've shown to have pretty deleterious impact on our societies. Critical thinking, of course, means think about where stuff came from. Think about who's saying things. Ask about corroborating evidence for assertions that are being made. We don't do enough of that. We should be teaching people to do that. And that's just part of the more general notion of digital literacy. Do you understand what risks you're taking when you're online? Do you understand not to click on random attachments and emails that have shown up? You should be a little suspicious about the kinds of things you encounter online, for the same reason you teach young people to look both ways before they cross the street. The next issue here, which is trying to deal with bad behaviors on the internet, including criminal behaviors or other harmful behaviors. The big problem is that the internet, by design, is non-national in architecture. The addressing space is not based on country codes. There are country codes in the domain name system, but there are also generic domain names like .com, .net, .org, and so on. And so this whole system is not like the telephone network, which had an addressing structure that was very country-oriented, national structure, whereas the internet is very international, or at least transnational in character by design. That was a very deliberate choice that Bob Kahn and I made in our initial work. However, now we have the problem that we have harmful behaviors on the net, and those behaviors may have perpetrators in one jurisdiction and victims in another, often across national boundaries, which means we now need to deal with international law enforcement. And at the moment, we have only weak mechanisms to accomplish the objective of identifying harmful perpetrators and to bring them to justice. So that's going to require a substantial amount of cooperation and collaboration on an international basis, and the development of governance policies in order to cope with that. The next bullet has to do is really a message for people who are responsible for developing software. It's my view that most of the bad things that happen in the network, especially the attacks from hackers, are a consequence of bugs that are being exploited in the software, which means that the tools that we use to develop applications are weak when it comes to exposing bugs before they get out into the field and are exploited. And so I'm feeling the need to press the academic community to build much better software development tools or software development environments so we can minimize the bugs that get out there. And of course, we know that we won't get to 100%. And so the next problem is, how do we make sure that it's possible to upgrade software safely and securely when we find bugs? This is especially important in the IoT space, because the software in those devices is expected to run more or less autonomously, unless, of course, it's got bugs, in which case it may fail in some fairly spectacular ways. The most vivid examples, of course, might be autonomous vehicles that are, running a boatload of software in the car, and when it doesn't work, bad things could happen. So we really need to focus on improving our software quality. And finally, that raises the question of ethics and software-based systems in general. If you're building software-based systems, I think that programmers and companies that produce a lot of software or services based on software should feel a very strong ethical responsibility for making sure that those 6 desiderata that I listed at the top, reliability, safety, privacy, security, interoperability, and autonomy, are properly catered to. And that I think that it's not enough to insist on ethics. I think we also have to have some enforcement mechanisms, or let me say incentives, for ethical behavior in this space. And those incentives could vary from people being, having liability for failure to observe ethical and safe behavior, all the way up to potential criminal prosecution. Next slide. This gets to yet another very serious problem, one which is become much more visible, I think, in the course of the pandemic, which has been raging across the planet for the last year. And that is that the internet has become an essential tool for keeping people connected when we're not allowed to be physically in proximity to each other. Unfortunately, there are several things that have become quite obvious. The first one, of course, is that not everyone has access to the internet for a variety of reasons. Either it just physically isn't available, there's no infrastructure there, or it's too costly and can't afford it. Maybe the government doesn't want you to have access to it, or it sets up monopolies that are unwilling to provide service where it's uneconomical in the rural areas. Or there may very well be that there's nobody there who could operate the network, even if you could install it or make use of it, because they don't have enough skill to capitalize on access to the internet. So there's a bunch of features that I guess we shouldn't call them features, but there are problems associated with the digital divide that it either created or exacerbated. And so overcoming all of that, I think, is a very important objective. You'll see it implicit in the Sustainable Development Goals in the UN, and certainly in the initiatives of the Internet Society and elsewhere. People-Centered Internet is another organization that's focused on this, as is the Marconi Society, which I chair. So these are all things that I believe all of us could try to commit to and support, which is to shrink that digital divide and make the internet useful for everyone. Next slide. This was just a surprise for me, discovering how much undersea cable has been installed over the past 20 years or so. There are places, islands in the middle of the Pacific, for example, that are interconnected with fiber that I never expected would ever be connected. The costs have gotten low enough now that in some cases, companies like Google build their own cable as opposed to having to join with others in order to afford the cost. So we're seeing a substantial amount of connectivity growing up now with subsea cables. But the next slide will tell you where else we're going. And that's the low Earth orbiting satellites. Starlink and O3b, OneWeb, and Kuiper are all examples of major low Earth orbiting satellite initiatives. Probably the most advanced are Starlink and O3b, both of which are in operation. O3b is a medium Earth orbit. It's about 8,000 kilometers. The Starlink system is more like 700 to 1,100 kilometers, so the latencies are quite low. And the number of satellites is extraordinary. The projected total number for Starlink is 24,000 satellites in low Earth orbit. It'll be almost impossible to avoid internet access as a result. Some of these will be polar orbit, and that means that even the North and South Pole will be connected. Some of the performance I've heard from Starlink is in the 300 to 400 megabit per second range, which I thought was pretty amazing. So, we're in, I would say, very good shape, assuming that these systems both work as planned and also are affordable. That still is to be determined what the economics of these systems are. But if they can be made affordable, then access to the digital divide will shrink pretty dramatically once these are up and operating. Next slide. I don't need to tell you that there's an incredible number of devices with programmable devices now that are part of the internet environment. I'm not going to step through all of these. It's just to illustrate the fact that things that didn't used to have programmability do, like light bulbs, for example, and refrigerators, and even a surfboard, which has a laptop embedded in it, so the guy that's out there waiting for the next wave can surf the internet while he's waiting to surf the ocean. That's a real product that somebody's making. So we will see more and more, millions, maybe billions of these devices over time. And again, I need to remind you that they're full of software, and software is often full of bugs, and bugs are exploitable. And so there's some risk associated with these devices, despite the fact they also offer convenience that we might not otherwise have. Next slide. Well, this is just a list of devices again. I don't really have time to walk through each of these. I'll let you speculate. Although I have to pick out the internet-enabled sock. I thought was kind of interesting. What if it had an RFID chip on it? And if you could transmit a blast of RFID sensing in the house, you might be able to get a signal back from the sock that's under the sofa in the living room, which means I've solved the problem of the missing sock. And I think that would be a massive contribution to future history. But the idea here generally is that these devices, once they have software capability, will increase their utility. Although I have to say, one of the things I worry about is if the refrigerator and the bathroom scale are on the same network, and the refrigerator is paying attention to what's being weighed on the bathroom scale, the refrigerator may refuse to open because it knows you're on a diet. That's not a great future. Next slide. So I thought I would just spend a few minutes on the interplanetary extension of the internet, because this is not a speculation that's actually happening. Let's go to the next slide. So the work began in 1998 after the arrival of the Pathfinder lander on Mars in 1997, which landed 20 years after the previous successful landings in 1976, the two Viking landers. Then after that, for 20 years, nothing worked, everything crashed or missed the planet. But in 97, we landed successfully. So if I could have the next slide. Since that time, a number of landers have arrived, and there are more coming this month, as many of you may know. Coming up on the 18th, the Perseverance lander is supposed to land on Mars, and there are others that are in orbit from China and from the UAE, I believe. So what's important here is that we met in 1998 at the Jet Propulsion Lab and asked what we should be doing in order to be prepared for the needs of the next 25 years. And so we were trying to look ahead 25 years to what would be needed. And we said, why don't we figure out how to build an interplanetary backbone network to support manned and robotic space exploration? And indeed, that's exactly what has happened. All of these various landers are using store and forward relay technology now around Mars in order to transmit data back to Earth. So if we could have the next slide. What we're hoping to do, we are operating on the International Space Station. We have prototype software running on Mars and several of the rovers and the orbiters. We've standardized the interplanetary protocols, which, by the way, are not TCP/IP. We discovered very early on that the delays for internet or delays for transmission in interplanetary space are so large that the normal TCP flow control and the problem of planetary rotation and disruption of communication was such that we needed a new class of protocols that handle delay and disruption more effectively than TCP/IP. So we developed a whole new set of protocols we call the bundle protocols, and those are now standardized by the Consultative Committee on Space Data Systems, which is a UN agency of spacefaring nations. It's also being standardized in the Internet Engineering Task Force for terrestrial use. The current hope is that we will use these protocols for the return to the moon, the Artemis program. The space agencies, NASA, JAXA, the Korean Space Agency, CARI, and ESA in Europe are all collaborating to standardize and use these interplanetary protocols so that we will have a potential for a common backbone network. This image that you're seeing right now is simply sort of a fanciful point that as missions, scientific missions go on their explorations, as they complete those scientific requirements, they can be repurposed. Those spacecraft can be repurposed as nodes of an interplanetary backbone. So literally, we will grow the interplanetary backbone mission by mission as spacecraft become available and can be repurposed as nodes in the backbone network. I think that's the last slide.
Great. Thank you so much. Very informative. And it's interesting because I've been actually making the list of who's going to ask questions. And Pablo asked, actually, one of the last questions was on the interplanetary internet. So I'm hoping that addressed the issue by Pablo. But let me go back to the first question that was asked. And I'm going to go back to the slide that she's referring to. Let's go back a little bit further. And okay, so Sally DeFore asks, how much of the unfinished business were you able to imagine, if you like, right at the start? So she's, and it's hard to predict the future, but was there anything within the three of you that considered that could happen, or where was the philosophical parameters that you were working with?
Well, honestly, I don't think much of this really showed up, with one exception, security. And of course, some people will smile and say there isn't any. First of all, remember that this project was intended to be in support of the U.S. Defense Department's command and control network. It was intended to be, it was an experiment to see whether we could use this packet switching technology for command and control. And at the time that we were doing that, hearing some interesting background noise, at the time we were doing this, of course, we had the ARPANET, which was a very successful demonstration of packet switching, and then the internet. And wow, I don't know what to say about the background noise, folks. In any case, when Bob and I began thinking about how this network would be applied, we concluded that we needed to release the specifications for it publicly so that any country in the world would have access to it. And the reason for that is we didn't know which countries would be our allies in the course of history. And so we thought we had to release this publicly. Of course, some people say, how could you do that? And Cold War, and the answer was, well, we just did it. We didn't ask for permission. Sounds like somebody is preparing breakfast.
Okay, the next question comes from Diane Olivan. She asks, achieving digital literacy, particularly in the global south, requires institutional and systematic change. However, most actors in these institutions, that is the oppressive governments, the dictatorships, actually benefit from proliferating misinformation, disinformation. What do you think should be the focus of us working in IG digital rights, especially now when there is a concerning increase in the use of these platforms to stifle freedom of expression and experience?
Yeah, it's a tough problem. My reaction right now is that the countervailing attraction of internet, of course, is commerce. And the fact that enormous amounts of new business and now old business are being conducted in this online environment, even in China, where we all have seen this so-called Chinese firewall inhibiting the ability of Chinese citizens to get out to other facilities. The network is still there because the Chinese need to advertise their products and services to the rest of the world. So there is a kind of, even though there may be a desire to somehow control what citizens get access to, both domestically and externally, there's also a motivation for staying connected somehow in order to take advantage of the commercial value of being online. And so in terms of trying to counter the oppressive desires of some governments, about the best I can say is that we should still seek to keep the network as open as possible. We should still try very hard to teach people how the network is used and abused. That may be difficult to do in some oppressive regimes, but again, to the extent that we have the ability to provide access to that information. I mean, some of you will know that virtual private networks are a trick that often gets used to get past firewalls. It doesn't last for long, but I think there will be a persistent effort by citizens in oppressive countries to try to reach out to the rest of the world. And a good example of this is Cuba, where for many years there was very little or no access to internet, but there were people who would get access somehow, maybe physically coming to the US and then coming back to Cuba, and they would copy stuff off the internet and then share disks with people in order to provide them with information. So I think all we can do is work very hard to keep the network as open as possible and to teach people how to think critically about what they're seeing and hearing, even if the governments don't want them to learn how to do that.
Okay, thank you. I have a question from Liliana Pakova. She asks, do we need jurisdiction clarification in the national legislations for internet crime acts? As you mentioned, the perpetrator is in one country, but the victim is in another.
So there has to be some kind of agreement. There exists one called MLAT, which is a mutual law enforcement treaty that is very clumsy and slow. It's not adequate to the kind of things that happen at internet speed, but it's representative of an attempt to deal with countries that recognize that there are harmful behaviors and that some of the perpetrators are in one jurisdiction and the victims in another. My sense right now is that we are only at the very beginning of trying to understand what kinds of agreements we might need in order to, if the countries agree that the tracking down harmful behaviors or perpetrators on the internet is in their best interest, then we will see treaty-like agreements. There are a number of attempts that have been made to build such things. The Budapest Convention being an example of that, but there are others. There's a global commission on the stability of cyberspace that's come up with a list of a dozen or so norms that they think they're not treaties, but they are suggested norms of behavior. Example, and one of the first ones said, why don't we treat the core public components of the internet as protected in the same way that we don't bomb schools and hospitals? We should say that you shouldn't attack or disrupt the fiber or disrupt the routers or disrupt the domain name system. And we might have more global agreement on that norm, even if it's not an enforceable treaty, but norms could become treaties over time. So we have a lot of work ahead of us to reach agreement that it's in the best interest of countries, hopefully in a multilateral way, to cooperate with each other in order to protect citizens from harm. Unfortunately, in some oppressive regimes, the harm that is of concern is protecting the government, the regime, as opposed to protecting the citizens. There's not much we can do about that except job owning at the moment.
Great. Thank you. I got a question from Alfredo. His question is, what are your thoughts on the new IP standards?
Well, I don't think that they are going to happen. I think that this was, first of all, from a technical point of view, it made very little sense. There were arguments about, holograms and, real-time surgery and things like that. And the speed of light delays are a bit of a problem there. We don't know how to double the speed of light. So I don't think that the two proposals held much water at all. I believe that what was intended is to try to get more control over internet by trying to propose a new set of standards. They went to the Internet Research Task Force, and the Research Task Force said, well, we'd be happy to pursue some of these ideas if you'd like to. Some of them are out of scope for us. And the group that was presenting the new IP protocols took that as rejection and then went to the ITU. My belief is that was deliberate, that their intent was to try to shift internet evolution into the ITU-T standards making activity. I don't consider that to be a useful thing. I think we should stick with what we've got, IETF and the World Wide Web Consortium for the web-based protocols, and IEEE for some of the basic radio standards for Wi-Fi and similar kinds of applications. ITU-T has a role to play, and ITU-R especially, the radio spectrum and its allocation. But I believe that was largely a political maneuver, and I don't believe that it has reached much success.
Great, thank you. You mentioned in your slides, you were talking about the future of the internet and different technologies, and we have 3 people on the call that are from Puerto Rico, and they experienced the Loon project, which was a project for Google. Any comments on what's happening with Loon?
Well, Loon, as many of you may know, has finally reached the end of life. It was an audacious project. We supported it for 10 years at Google, and the X organization spun it out as a separate organization. It just was not able to generate a revenue stream soon enough to be self-supporting. And at some point, you have to conclude that you can't find a business model that would support it. It developed some amazing technologies, and I believe some of those will persist. Most significant of which was the Minkowski routing system, which I think is applicable to a variety of very complex situations where you have connectivity which is dynamically changing. Remember, the balloons were free floating, and so figuring out where they were and what the connectivity was is hard, and would be applicable to similar kinds of things, even in ground-based systems. Imagine you have automobiles driving around and their connectivity is going to change from time to time. That kind of routing capability might be very applicable, and I see some space-based applications where that same technology might be quite useful. So Loon's technologies will persist even if the company doesn't.
Great. Another question from Pablo. I think you addressed his interplanetarian issue. He asked here, he would like to know more if the civil society will have any participation in the decision-making for the internet in the near future.
Well, I believe it already does, because there is, within the ICANN space anyway, there are decisions that are made about domain names and IP address allocation, and civil society and governments have a role to play in developing those policies. They don't necessarily have a role to play in enforcing them, but they certainly should have a role to play in their development. I believe the same thing is true for the UN environment. That's why we have an Internet Governance Forum. It's not a decision-making body, but it should be one which surfaces issues and tries to influence the policy-making bodies based on the results that are surfaced in the IGF meetings. We have, in addition to the annual International Governance Forum, Internet Governance Forum, there are also national and regional ones. And those two have the potential for influencing policy making and enforcement.
Great, thank you. And I'm just looking on I have more questions in the chat. We have roughly 14 minutes left to this session, if you're okay. Kathy Bogart asked a question. Oh, I thought the session started. Sorry, she came in late. I'm just reading her chat. So anyone else have a question for Vint? What I'll do is pull out Dr. Pablo Rodriguez. Pablo, I'm just going to unmute you. Just looking for your. Right, here we go. Okay, and I'm unmuting you. Pablo, can you speak?
I can. Thank you very much, Professor Vint. It has been a real pleasure to have an opportunity to speak with you, and I'm so looking forward to be able to see you personally and give you a big hug and stretch a hand. Referring to the Interplanetary Internet, as we have been participating in ICANN, do you foresee that we will be able to participate further in this interplanetary coordination and protection of the internet? Or at this point, I can imagine that this might be a state-run project that at some point we will be able to participate. What are your thoughts on that?
So, well, there exists a group that was sponsored by the Internet Society called the Interplanetary Network Special Interest Group, IPNSIG.org. We are having workshops coming up soon. If you go to IPNSIG.org, you'll see what the schedule is. We invite participation. We have about 800 people who are involved in the special interest group now. Some of them are actively implementing the interplanetary protocols and testing them, mostly terrestrially. We've just recently, literally just in the last couple of weeks or so, gotten implementations of the bundle protocol running on all three clouds, Azure, Google's cloud, and AWS. The reason that's important is that once they're running in the cloud, then we can make access to them available to mobiles and laptops and things like that. And the idea here is to test the protocols and their, the management of the system at scale, so we can surface problems that might arise. We can fix those problems terrestrially more easily than we can a spacecraft that's halfway to Pluto. So we're very interested in having public involvement, either very direct involvement in the development and evolution of the protocols, or more tangential involvement by simply exercising them, so we can measure and see how things work and what breaks. So please go to ipnsig.org and follow along and volunteer if you're interested.
Thank you so much.
Great, thank you, Pablo. And for everybody's benefit, Pablo will be speaking in a couple of weeks on infrastructure. So he'll be speaking with Allison Moore. They'll be talking about .pr and also .ca. So thanks again. And Pablo's on our advisory council and one of the sponsors of the VSIG. Thanks again. I've noticed that Olivier has joined us. Olivier Crepin-LeBlanc. I'm just going to unmute him. Okay, Olivier, do you have your audio? Okay, I'm just giving him a second here.
Well, while you're doing that, let me just suggest that we didn't say anything about 4G, 5G, and 6G. Yes. I feel compelled to at least say something about that, since it's become such a hot topic. First of all, the 5G and whatever 6G turns out to be, there's a lot of debate about that. 5G has a couple of properties that are of significance. The first one, of course, is that it may have higher bandwidths, especially when it's operating at higher frequencies up in the 28 gigahertz range. But even at the 6 gigahertz and below, it may have increased capacity. There may be increased density of cell towers as a consequence of that. However, there's some features of the 5G design which I find disturbing. One of them is called slicing, and this basically moves us back into the historical virtual circuit or real circuit switching mode, where you're segregating at capacity or features of the underlying system in order to dedicate it to some particular function. Now, the arguments on the side of that are that, well, somehow you will get lower latency or higher bandwidth or some other desirable property. The thing I'm not very persuaded by, though, is that we've seen that by operating at wideband and doing pure packet switching, that everything gets better. And, you know, today you are running huge amounts of video traffic throughout the internet, and the reason it works is that we're using higher and higher bandwidths in the backbone and at the edges of the net, and it's an undifferentiated broadband system. And so I'm not a big fan of the slicing idea in 5G, and I believe it's a backward step, even though what it may do is give more control to those who are offering the 5G service to charge you for different kinds of service, and that bothers me. We're on that same path, apparently, going into the 6G. The other thing, which is somewhat disturbing, is that at least for a period of time, the 5G standardization looked like it was going to expose specific applications to for particular users. In other words, you would have to ask for a particular application through this 5G interface in order to get the right performance. And so you would have to be specifically saying, I want Netflix or I want something else, which exposes your privacy, because now you'd have to ask for a very specific service, not just a class of service, but a particular one. Now, as far as I know, that issue has been derailed, basically, but it's an example of this attempt to gain more and more control over what the users are doing. And I'm a big fan of this broadband open datagram style. Okay, now you have a question from Olivier, maybe.
Yeah, let's see if he's, I tried to unmute him. Olivier, are you there now? Okay, just on that 5G topic, we have a lot of resources we've put into our complementary resources for the students from GSMA, but we've also included a new module on emerging technologies, which is including IoT, blockchain, artificial intelligence, and I think he's there now. I guess it's good afternoon for you, Olivier. Can you say something?
Yeah, hi there, Glenn. Thank you very much, and apologies for this. I seem to be totally technologically challenged today in that I said, yes, I'm here. I clicked the thing and it opens half a dozen windows asking me to provide the authorization for a camera, for a snap camera, for a virtual for goodness what else. Anyway.
Yeah, I sympathize with you. It took me 15 minutes to get logged in this morning. This application is counterintuitive. Anyway, lovely to see you again.
I had a vivid memory of playing whack-a-mole lots of years ago. Do you remember, with a mallet, you have to press the buttons as quickly as you could, and this is what happened today. Anyway, just to pass on this, first, I was really delighted to see you here, Vint. The question that you answered with regards to 5G is actually interesting in that it's a recurring question, and would you believe it, actually did my PhD on something similar to this back in 1991, which was the reduction of delay in asynchronous transfer mode networks. Now, admittedly, it's not TCP/IP, it's ATM. It's a technology which I guess now just shows how old I am, I guess. But the thing, though, is the overall workings was that if you're going to start prioritizing traffic and prioritizing it across all of the network, you end up with every traffic wanting to be high priority and ending up with high priority traffic actually being slower than low priority traffic. So that just made it really, you know, pretty a terrible idea, basically. And the overall conclusion was that you just had to provision the network for having enough bandwidth. On a local level, perhaps, on a local link, so locally you might be able to prioritize a specific type of traffic over another. If you're going to deal with traffic, for example, as cars needing immediate responses from sensors and other vehicles on that one sub-network with direct mesh communication. But in a long distance, is just, I'm sorry, but that's my findings were that it was not workable. It took me several years to find that, and I thought this is great. So I've managed to design a great failure, and the response was, well, at least you proved it wrong. So that's it's good enough.
Olivier, if I could ask, interrupt for 1 second. There's something very important about what you just said, and it has to do with recognizing something that doesn't work. You know, we tout our successes, and we often don't publicize our failures. I'm not suggesting, by the way, that what you did is a failure. In fact, what you did was expose the flaw in the reasoning, which I think is really important. It should have kept people from going down the same you know, blind alley. Unfortunately, we make this mistake repeatedly. I have seen several iterations of the let's allocate things by priority and try to get it to work. We have a system in the US where I live that some parts of our highways are paid for priority. You pay for the privilege of getting priority. And it's only 1 lane wide. And so if anything happens, it jams up. It's worse than being in the other part. Same problem.
Indeed, very much so. Indeed, yeah, totally. So unfortunately, Glenn, I gather there was a question that came to me, but I was on another call at the time. I'm being hounded with calls at the moment, so I just missed that little part.
Okay, I'm looking for it in the body, but I don't see it. But I thought since you're online, I dragged you into the question pool and ask your comments. I have to point out, Olivier, your fantastic presentation, which we recorded in Group B, is available for all the students to see as well. And same as the session you did with us in Montreal, our face-to-face School of Internet Governance. But thank you for joining us today. I think we just have one more time for one more comment from Rakesh Mohan Bhatt. He makes mention here, Vint, when the perpetrator in one country and victim in another, it means IG definition changes when it goes beyond the boundaries. So how do we make standards on this? And I think you alluded to something on that, but I think, I guess he's alluding to maybe more international standards.
Well, I think that the end result will probably be a collection of agreements, some of them multilateral in character. I don't think we will have a uniform agreement across the world of what's acceptable and what is not acceptable behavior. I think that's unlikely. But we have seen common agreement, for example, international law of the sea, which I'm embarrassed to say the US hasn't signed for reasons I don't understand. Similarly, there are agreements about what is or isn't acceptable in space or in Antarctica and so on. There's evidence that it's possible for us to come to broad agreement on what is acceptable and what is unacceptable behavior. But it probably won't be 193 countries signing on. But wherever we can, I think we should try to reach agreement, because we want people to be safe as well as feeling safe in this online environment. To the extent that they both don't feel safe and are not safe, they will eschew its use, and that will, I think, delete or at least reduce the value of the system, because its value is participation by everyone. So I think we are all faced not only with the technical challenge of making things safer, but with the legal and policy challenge of making things safer as well.
Great, thank you. Well, you know what? This has been a great session, and I do apologize for the challenges at the beginning, but I think we worked that out according to our time. One thing I learned today, beyond many things, was the fact that my weigh scale and my refrigerator have a battle. Now I have solved the problem on my missing sock as well. So that is something with our 5 Internet of Things, we'll have that solved. Again, I'll just turn over to Alfredo for closing comments.
As you can see, it's a challenge just to unmute. So thank you, Vint, for your excellent presentation and the exchange with the participants, and thank you to all the participants for the great questions. Just to let you know, this recording will be available about 1 to 1.5 to 2 hours after we finish the session. And Vint, it has been an honor and a pleasure. I'm not sharing my video, so you can't see me, but we met a few years back in an ARIN meeting. I was a fellow for a couple of those, and back in ICANN 53 as well. So I appreciate your willingness to join us and to share your past experience and your insights on the future of the Internet. Glenn, back to you to close this up.
Okay, thanks everybody. Don't forget, next week we have Nick Smith and Keith Dravik on the session. We have a complete lineup for every Monday, and we did listen to the challenges today, so we'll make sure that this doesn't happen again. But thanks again for your time, and again, thank you, Vin, for joining us today. And that concludes the call today. Thank you.
Thanks so much. Bye for now.
Thank you. Bye-bye.
Bye to all.